Okay, so today, fast gradient echo. So what we did last couple days was fast spin echo. So fast gradient echo is another extremely common sequence, and we'll just start off with some reasonably fast ones, and then we'll finally get up to EPI, which is like really fast. That's the really fast gradient echo. So today we'll talk about sort of pretty fast gradient echo, and there's two different kinds of it. There's coherent and incoherent, and the coherent ones are probably less familiar because they're not actually used that often. And they have, the problem with these things is always they have all these ridiculous acronyms. So the coherent one sometimes is called GRASS, which means like gradient recalled something in the steady state. So both of these are what we would call steady state. So that you remember when we talked about like imperfect 90-degree flips, you have to do several of them until you get to a steady state. Well, the same thing happens with fast gradient echo. It takes a little while to sort of get to the steady state, but then you're in the steady state. So you'll see a lot of sort of SS for steady state in there. And sometimes this one, on the Siemens scanner, this one is sometimes called FISP. I can't remember what that stands for. Sometimes it's called SSFP, which is an acronym from probably like the 1950s or something. That's steady state free precession. That's SSFP. And then there's another version of it called PSIF, which is FISP spelled backwards. But all of those are coherent fast gradient echo. And then much more common are the incoherent ones. And probably the most common name for the incoherent ones is flash, which means fast low angle shot. And we already talked about the equation for that one, and we derived the equation for the echo amplitude, and you used it in the first homework. But sometimes this one is called SPGR for spoiled grass. So that's spoiled grass. There's a couple, or sometimes it's just called fast gradient echo. But then there's a version of this one, or it's kind of like a combination of both of these two, which is called MPRAGE, and we'll talk about that. So that one's magnetization prepared rapidly acquired gradient echo. I looked up what it meant. I never knew what it meant. I learned the word without knowing what it meant. So, and that one's kind of like a different one. This one's a non-steady state, but this one's extremely common. This is probably one of the most common structural scans that we use at the MRI center, and it's used all around for sort of basic gray-white contrast, just to make something that looks like what you think of as a brain, with the white matter sort of lighter than the gray matter. So we'll sort of build up to that one, but we'll start with the coherent ones. So even before the coherent ones is slow gradient echoes, because remember we talked about slow spin echo. Back in the day, they started off with slow gradient echo. So this is a 2D sequence. So 2D sequence. You can do it in 3D also, but I'll just draw out a 2D one. And so slow gradient echo is basically, just one pulse and record some data. So, we do one pulse, say, we could do a 90, and then we pick out a slice and then sort of fix the effect of having picked out the slice. So that's GZ, here's RF in, what we're sort of sticking into the brain. Here's the phasing code direction. And the phasing code direction is we pick, one of these settings of the phasing code gradient to wrap up stripes in the, horizontal stripes in a Y direction. And then we do a readout. And the readout, first we go to the left side of K-space, and then we go across K-space. And in the middle, we get a gradient echo. So when we do this RF pulse, there's a big FID, which we ignore. And then here's the actual sort of thing we're recording. So that's our gradient echo. So, and so this is our, slice select. This is the phase encode. This is the readout. And then we wait a long time. So that's why it's slow. So for instance, if we did a 90, say we did a 90 over here, well, then it's going to take, a couple seconds in order for that to recover. And so we wait a long time and then do, another 90. So that, you can still do this. There's certain reasons you might want to do this when you want to get this sequence is still on the scanner. So you might want to do this if there's some sort of quantitative reason that you're wanting to do this, or you just want to get a signal that's sort of not contaminated by other stuff. So that's the slow gradient echo. But immediately people said, well, why wait around so long? Can't we do something in the interim? So you could do like one slice here and then do the other slices, but even so, if you're waiting a second or two, it's still going to be a lot of dead time. And you could make this, depending on how you set up your TR and TE, you can make this T1 weighted. If you do, a TR that's not too long, so that you get some T1 contrast. And you can make it T2 weighted if you do a TE that's pretty long, so you get some T2 contrast. And you can make it proton density if you do like a really short TE. So you can, even though it's very slow, you can sort of make all different kinds of contrast from it. So we'll call this slow gradient echo. Okay, so now what was kind of the first thing that was developed even before Flash? So like this grass idea. So people were already in the mood for spin echo. And so what do you do with spin echo or fast spin echo? You do an RF pulse and then do a 180 and then you get the spin echo. But then you've still got some magnetization left. And so what you do is you transverse magnetization. So it might be hidden, but it's still there. And so you kind of patch up whatever you did so that you can record another echo, a train of echoes. And so the idea of grass is, why don't we do the same thing with a gradient echo? Because we already said you could do something like this. You could make like a train of gradient echoes if you just sort of reverse the gradient, go in one, like go positive for a while and you go over to the right side of K-space, and then if you go negative for a while, you could sort of come back across K-space and make another echo. So why not do something like that, but do it with with all the parts of it? And so we'll give an example of this is a grass type sequence. So this is so coherent fast gradient echo. So how do we do this one? Well, it's now we'll assume that we're, just like we did when we were deriving the equations, let's assume that we're in a steady state, so that we've been doing this for a while. And so here's that's what our RF in. And so what does that dash mean there? Assume in steady state. So we assume that we're in a steady state here, so we've been doing it for a while. So the first thing we do is just do an RF pulse, and then we could be doing this one is, so this one was a 2D example, so I'll make this one a 3D example. The only difference between 2D and 3D is that you just do some phase encoding, extra phase encoding on the second gradient. So here's the y gradient and the x gradient. And here's what comes out, RF out. Okay, so now basically we maybe do something like select a slice or a slab. So this would be slab select, because we're doing 3D. But there's already something different here, and that is we're already in the steady state. So we've already been doing this for a while, and so that means that there's some magnetization. There's some magnetization sitting around already, because we're in the steady state. Assume we're in the steady state. And so that means that, so remember, the reason this guy was only half as big in area, so the area of this guy, of the little corrector, was half as big, is because we were assuming that basically you can think of the RF pulse as having started from the middle of that RF pulse, because at the very beginning, not too many people are lined up with each other, and at the end, there's a lot more lined up with each other, and you can sort of approximate that by sort of starting the RF pulse, pretending like the RF pulse started at the very middle of it, and so then the amount that you have to actually fix starts from the middle. So, but the problem now is that there's already some magnetization there before we started, because previously we were assuming, like in this case, we're assuming there's nothing here. And since there's already something there, then we've got to do this. So we have to sort of like pre-break things that this part is going to break. And then we add more RF, and then we post-on-break things that we broke in this second half. So you have to sort of have a balanced setup where we take into consideration we've got some magnetization, steady state magnetization, coherent, steady state. Put that in there too, just for good. So that's one difference. That's not a very big difference. And then we have to do our phasing code. Since this is a 3D sequence, we have to repeat this thing for all the different settings of the z gradient, and then we've also got to repeat it for all possible combinations of settings of the y and the. So if there's like 256 of these and 256 of these, then we need 64,000 different combinations of these gz and gy, and then we do our readout. So go to the left side of k-space and then go all the way across k-space. But now, since we're going to try to save all our magnetization, we have to essentially fix the fact that we went across k-space. And so remember, this one is supposed to have the amount of area that has. Those are supposed to be equal. And so the idea of this last one is to put us back in the center of k-space, because we go to the left of k-space and then the center of k-space is right here. That's when the echo occurs. And then at this point, we're back to the right side of k-space, and so then this will put us back to the center. So at this point, we're back to the center of k-space. So back to k-space center. And then we just do the same thing with the other gradients. So I just patch everything back up again with the other gradients, so that, because this guy will put us off from the k-space center in the y direction, and this one would have put us off from the k-space center in the z direction. And so if we went that direction, then we got to go that direction. So if we chose that guy, then undo it by choosing that one, and same way for this. So those are all sort of paired so that they're exactly undoing what the last one did. And then pretty much you're ready to go again. And so here's so at this point we're ready to start again. So we could do another RF pulse, and so that would be like a little prefixer, and then that's a slice select one, so that's slab select. So slab select, and this is also what we call the partition direction. It's confusing, but that's just the second phasing code. Second phase. And then this one is phasing code. And this is readout. Okay, so now we're in a position where we can repeat. And so we could use a very short TR. So here's the TR. So TR, for example, 7 milliseconds. And then here's the TE down here. For example, TE, for example, 3 milliseconds. So, quite short, so that we can collect lots of data. So this sequence is pretty unfamiliar. Most people haven't even. It's been on the scanner forever. It was already there in the early 90s or late 80s or something. But people don't use it very much. It has a very strange look to it because of. So if you work through the equations, which we're not going to do, and I don't think I actually have ever worked through them, but if one were to work through them, the signal, which is the echo amplitude, equals some constant times the sine of the flip angle. That's the flip angle. And then this whole mess is 1 over 1 plus the cosine of the flip angle. So it's got the same things that the gradient, our original gradient echo equation has, this sine and cosine of the flip angle. But it turns out, because of what you're doing here with all these sort of fixing things, you end up with T2 in there, not T2 star. So the equation is plus 1 minus cosine of alpha times T1 over T2 over T2. Okay, so then that whole thing is also multiplied by e to the minus TE over T2. And so those are actually T2, not star. So that's kind of looks like a mess, but how can we simplify this down? Say you got the cosines and sines, let's just throw all those out. And so what do you have? You basically have 1 over T1 over T2. And so basically that's, approximately equal to T2 over T1. So that's roughly what the images look like. And if we just insert values of T1 and T2 for different tissue types in there, what do you get? So you get something, typical tissue T1, T2. So if we just say, like, what is the brain? Either gray and white matter of the brain. It's going to be something like 0.1 in comparison to fat, which would be brighter, 0.3. But the cerebral spinal fluid is going to be like 0.7. So this will have like massive contrast. I mean, that's 700% difference between those two. Huge contrast difference between the CSF. And so what it looks like is this absolutely glowing CSF, and the brain is the brain's almost black, and then you've got this glowing CSF around it. So it's sort of a strange looking. The first time you look at it, if you looked at MRI images, you go, that's kind of weird looking. So what do they use it for? So one of the things you can use it for is imaging the heart, because there you're interested in the actual fluid in the heart, and so it makes like an extremely. It's a very fast sequence, and so it makes it extremely good for imaging, like flow into the heart. I've used it for making movies of people speaking. So if you stick somebody in the magnet and have them, say like cha 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 or t t t t, just to see like what's going on with their tongue, you can do this image fast enough so you can get like 5 or 10 images a second, so very rapidly. And so, because you can make these, you can squish the TR down, very low, and then you can actually, since there's a lot of water in the tongue compared to the inside of your mouth, which has almost no water in it, you can very clearly see the tongue accurately moving and touching different parts of the inside of the mouth. So it's also been used. There's a sequence called, I don't know what it stands for, BOSS. But there's the steady state in there. It's also been attempted to be used for functional MRI. So it doesn't work that well yet, but people have been, there's a subfield of people trying to use this to do functional MRI imaging as well. So just be aware of that. And in comparison to regular functional MRI, where we just kind of we don't try to save the signal. So what are the issues about a sequence like this? Well, when you're doing this and sort of patching up the magnetization, little imperfections in the gradients can lead to various kinds of artifacts, because with our standard MRI, a lot of times we just try to spoil, spoiled grass. So this means spoiled. What does that mean? That means like sort of just try to hit it with a gradient, get rid of it, and let's start from scratch again. In this case, you're collecting hundreds of echoes and patching them up every time. And so after that, if something is not right in your patching, you can cause problems down the line. And that's the kind of problems that they have with functional MRI, doing this with functional MRI as opposed to just sort of doing a pulse, getting some data. Let's crush whatever's left and start from scratch. So that's a strange sequence. Most people haven't heard of it or never used it on the scanner. I don't think any of the people that use the scanner center have ever used it, but there it is. So that's coherent, steady state fast gradient echo. And we could have called, we could have called the fast spin echo coherent also. It's the same. It's coherent in a similar way, where we're just patching up the magnetization that we have left over from the previous echo and then getting another echo. Okay, so any questions about coherent steady state fast gradient echo grass? Okay, so now, yep. Oh yeah, okay, sorry, I didn't put that up there before I erased. Yeah, so this alpha, in this kind of sequence, it can be higher. A lot of times it would still be relatively short to avoid getting too much RF, because you're doing so many zillions of them. It might be like 30 degrees. But in the next one that we're going to talk about, the spoil grass is typically much smaller, like 7 degrees, very low. Here you can afford to, in this kind of sequence, you can afford to go up to a higher flip angle, because you're patching up the magnetization, you're not just trying to throw it out. And so, but yes, often you're doing so many RF pulses, you might not want to have it be a full 90. And if you put in like a 90 over here, you'll see, if you put a 90 to the equation, it will still work. You'll still get a signal. Whereas if you put a 90 into the equation for the incoherent one, you pretty much won't get a signal at all. Okay, so now one of the most common sequences, because every single localizer, when you first stick somebody in the magnet, the first thing you do is just do a quick and dirty localizer to find out where their head is. That's going to be one of these flash spoiled grass. And so how does the spoiled grass work? So I'll do a 3D example of that. So this one is called, flash. That's probably the most common word that people use for this. So what is it? It's incoherent steady state fast gradient echo. And this is a 3D version of this. 3D version of this. So this one is quite simple. So it you just have again, we're assuming that like we're in the steady state, so we already have done this a whole bunch. Takes like 10 or 20 pulses before it gets to the steady state. And in this case, we are assuming that we've gotten rid of all the magnetization, and so when we pick out a slice, all we have to do is just do a half a fixer after it. And this this guy, might be a relatively low angle, and the reason for that. So this is R F in, and here's the Z Y and X gradient and RF out. And the reason for that is basically we're not wanting to kill our longitudinal magnetization. So if this is our flip angle, if we go all the way to a 90, we'll have no longitudinal left. So that's M L, and this is M T. So if we just do that, we get a sizable amount of transverse here, but we've hardly cut our longitudinal at all, and so that's why we do like a low angle. And then we've already drawn the sequence a couple times. So if it's a 3D sequence, so we would do a whole bunch of different phasing codes on the partition direction, and then a whole bunch of phasing codes on the phase. So partition is the second phasing code, and then a whole bunch of different gradient settings on the regular phasing code, and then our readout, we go to the left of k-space, and then go one line across k-space, and that gives us an echo, our gradient echo that we record, and we just ignore the FID that comes out here. So now we wait, we record a reasonable amount of the echo. The echo is more or less died away, but there's still a lot of transverse magnetization there, a lot of hidden transverse magnetization because it's T2 star, and we haven't sort of fixed the static gradient offsets. And so now what? So now the incoherent part. So how do we sort of mess it up? And so the two main things that we do. So one way of messing up some leftover magnetization is we can dephase it. And so what we do is we just put some gradients on. So we could put like a really big gradient on, and what does that do? Well, you've got some magnetization stripes. You're at the right side of k-space, so maybe there's 128 stripes in spin phase going across in the x direction. What if you turn on a big gradient like this? It will like wrap it up to 768 stripes or something. It's like a really high number of stripes. And what does that do? That's like a really T2 star or a T2 star. It really sort of reduces the signal from it, because as you wrap it up, more and more cancellation occurs because everybody's out of phase. And so you can sort of think of that as you call this, a spoiler. And so what you're doing is you're just trying to spoil the magnetization, just mess it up, any leftover magnetization. Now, if you just do exactly the same size all the time, well, then sooner or later you could run into some kind of problems down the line. And so a lot of times what happens is you just pick random. So you could pick a random amplitude. To just kind of mess it up. So just sometimes mess it up a lot, sometimes mess it up less, and that just kind of like sort of just gets it out of there, just gets it out of your hair. And so then what you can do is you can do another, at this point, you can just do another RF pulse, another alpha pulse, assuming that you kind of wiped out any magnetization that was still there. And so then we would, do another slab select. So this guy would be, slab select. So this is the partition direction, or the slice direction, or the partition. And this is phase. And this is readout. Okay, so now we're ready to do, just repeat everything. And so now you have another guy here, another one here, and again, it's very fast. And another, readout here, and another spoiler here, and another echo here, and another FID here, which we're ignoring. So basically, then you could just keep repeating there. So here's the repeat. So again, the TR would be low, like the TR is something like 7 milliseconds. And the TE would be even lower, like 3 milliseconds. And then there's one more thing that we typically do, and that has to do with the phase of the RF pulses. And so if this RF pulse has phase n, then so what does that mean? That means, like, where are you around the circle of phase? And what is the circle of phase? The circle of phase is perpendicular to the bore. So if this is the bore, the circular phase, the circle of phase is a plane perpendicular to that, and somewhere around that 360 degrees, you set the phase. But what does the phase mean? The phase means where is your oscillation with respect to time equals 0 set by the transmitter. So when you turn the transmitter on, the transmitter will say, I'm going to start with the magnetization of this 123 megahertz signal pointing in that direction at time t equals 0. And then the transmitter keeps really good time, and so what you can say is, well, I'm going to turn on this RF pulse with a phase of 90 degrees. And what does that mean? That means that I'm going to turn it on with a quarter cycle ahead of where I turned it on the first time when I defined t equals 0. So that's what the phase means. And so normally you might say, well, let's just stimulate with the same phase, because that would be the best way to sort of keep the signal going. But if we don't want to keep the signal going, then let's stimulate with a different phase. And so if you do a bunch of equations, it turns out the best way to spoil your RF, your transverse magnetization is to stimulate with whatever the phase was last time plus, either 117 degrees or 123 degrees. So, one of those. So if you do that, you have the best chance of messing up and spoiling your phase from the previous one. And this thing is called RF spoiling. So we do that too. And that's available on the scanner. You can click it off and see what happens. The images don't look as good. So this guy was kind of the gradient. spoiling, and this guy is, RF spoiling. So we're making lots of efforts to spoil things. And so this is very common sequence, and you can get different contrasts out of this sequence. Remember that what the graph looked like for this sequence looks something like one tissue type, say the gray matter. If you plug in values into that equation, looks something like that. So then maybe that's the gray matter. And then if you look at the the white matter, you get something that looks something like that. So this is gray matter, white matter, and what's down here is the flip angle. And then this is echo amplitude. Echo amplitude, also known as pixel brightness. And so what contrast you get with this is quite variable. If you go to a very short, a very small flip angle and a very short TE, you can get proton density. If you go to this one, what if you pick this one? Well, then you would get like zero contrast between the gray and the white matter. And what if you picked something over here, and if you pick something less than where they cross, you'd end up with the white matter being darker than the gray matter. So you'd end up with, like a negative number there like that. But then, there'd be a maximum in the contrast. This is white matter minus gray matter. So if you do white matter minus gray matter, this is going to be your optimal flip angle. Somewhere up here is where you're going to get the biggest contrast. Somewhere like that. And that might be a flip angle of, say, like 7 degrees or something like that. Small flip angle. So you can get all different kinds of contrast here, but this is the one that would be commonly used, like a small flip angle that results in the white matter being brighter. Okay, so that's our regular flash spoiled grass scan. But early on, people figured out, let's do this is like like I said, like slow gradient echo, easy to understand. Fast gradient echo, a little bit more messy because we've got this spoiling going on. And then what about MPRAGE? So MPRAGE is a non-steady state scan. And this is like, we've just slowly hacked away to make something that works better, but then it sort of gets kind of a little ill-formed. And so what does it mean that it's non-steady state? It means like something is changing across the collection of data. So here pretty much, once you get into the steady state, you can just collect a pile of data. So what does this sequence sound like? It just sort of sounds like, it's just continuously collecting data. You can hear the gradients a little bit as it's stepping through these gradients. You can hear it going like, you can hear the gradient getting a little stronger. But the gray-white contrast is not that great. And so some people said, MPRAGE, why don't we just try to do something that's like inversion recovery? And remember, what is inversion recovery? That we start at MZ0 here, and then we go down to minus 180. We do a 180 degree pulse, and then we let some recovery occur, and then we're hoping that some tissue might recover a little faster. And then right at that point, when one of the tissues is 0, so this is magnetization longitudinal 0, so when one of them is 0, then do another RF pulse, and then we get a lot of signal from the dotted one and not much signal from the from the continuous one. So that's, inversion recovery. But the problem with that is that there's only a moment in time when that occurs. So it's going to be and you have to wait a long time. This is like, this is like, like at least a second, 1, 2 seconds. So that's a really long time. And so there's slow inversion recovery. I have sat in the magnet in the 90s. It was for slow inversion recovery. Spent like an hour in the magnet just recording one image. But the guys who came up with MPRAGE said, well, why don't we just try to mash in inversion recovery into this? And so what you do is we do a, so now it's this gradient and the Z gradient and the signal that comes out and some space for a graph below. Okay, so here's the RF in and the Z gradient and the Y gradient, the X gradient, RF out. So the first thing we do now is we do an inversion pulse. And so an inversion pulse is, so if we haven't recorded any data, we do a 180. And since we're going to have a little bit of a gap in time, so there's a little bit of a gap in time here, like a second, something like that. That's waiting for some recovery to occur. We can do a good quality, an adiabatic 180. So, we can do a good quality. And I haven't talked about these, but pulse. Good quality pulse takes longer. But you have some time, so you can do a good quality pulse. So invert, all the spins, and then here's the non-steady state part. So what happens is we start off at MZ0, and when the 180 hits, we're going to go down to minus MZ0. And then we'll start recovering. And so what happens is we, recover for a while, but not too long, and then immediately start doing this. And so we'll, do an RF pulse, let a little bit of alpha pulse, let a little bit recover, do another RF pulse, a little bit recover. And so you just do a whole crap load of RF pulses until you finally get to the center of K-space. And then the hope is, right at the center of K-space, so this is the center of K-space, because as you'll see in the homework, center of K-space is very important for determining the contrast. And so you wait until you're hoping that the white matter got slightly above, this is magnetization longitudinal, so slightly above 0, so that there's a signal, but the gray matter got exactly at 0, and so that RF pulse that we're going to record a readout for through the center of K-space will have a lot of contrast, because there'll be no signal from the white matter, the gray matter, and there'll be a signal from the white matter. And so the idea is that there's another one that's really close, and hopefully that guy just exactly ended up at 0. But it's kind of weird, because what you're doing is you're recording some spatial frequencies that are not at the center of K-space with different contrast. And then you keep going for a while. You keep going for a while and record more, but you still haven't got anywhere up close up to here, and then stop recording. So stop recording, stop doing the RF pulses and just let that recover for a while, and then eventually do, recover for a while, and then eventually do another 180. So it's non-steady state because the magnetization isn't in some kind of similar form across each RF pulse. And so what does the pulse sequence look like? Not too much to it. We just have a bunch of alpha pulses, and these could be relatively sloppy pulses, even just hard pulses. So here's an alpha. And so what does this sequence sound like? So if you're in the scanner, I've sat in the scanner, you hear a little gap. Well, you hear this little gap in time here. So it sounds like, gap, and then there's some gap here too. And then you hear then gap, you hear a little gap while you're getting some recovery here with no recording and some recovery here with no recording. So you're not continuously recording, but the advantage is you've got much better contrast because of this. And so let's not even bother doing we're doing a 3D sequence, so don't even bother doing a slice select or a slab select, and then do our phase encode in the partition direction, and phase encode in the slice direction, and then do our readout like that. And the very first, and so what signal comes out? Well, here's our echo coming out, and here's the FID that we're not recording. So there's our echo. So in the very first version of MPRAGE, they put a spoiler in over here. But it turns out that doesn't work as well, and so the current MPRAGE doesn't have a spoiler. Instead, what it has is a fixer. So it has something that looks more like grass, but just in the partition direction and the phase encode direction. So the idea is that if we're going in that direction, then go in that direction, this direction, go in that direction, but don't do anything here. Don't fix the readout. So the contrast still ends up looking like flash, even though it's kind of like an ungainly combination of sort of inversion recovery, and then there's some non-steady state things going on, and then you're doing something that's kind of like grass. But it works great. Best gray-white contrast that you can get. And so now we're ready to do like another alpha pulse. And so just do the same thing again. Pick another partition direction. Pick another combination of phase encode. Go to the left side of K-space. Record another one. And then when you're done, kind of fix again. So if we're going, this way, then go that way, and then don't do any spoiler. No spoiler. No spoil. But the contrast, maybe just because you're no fixer, no fixer. Also no spoiler. Maybe just because you're doing no fixing here, the contrast ends up looking like flash, not grass. So, and then of course these would be these. So this guy, let's sort of annotate. So this guy, this echo is going to be this guy down here, and then there'll be a lot of time before we eventually get to the center of K-space. 100 echoes later, we get to the center of K-space, and so here's the alpha for the center of K-space. And so, we have our phase encode here, phase encode readout, phasing code fixer, another fixer here. And so say this guy is the center of k-space. So this is nice big echo for the center of k-space. So that guy, center k-space. So that guy, where does that guy go? So that guy goes right there. But then we're going to do, et cetera, collect some more until finally we get back. So there'll be more collection there. You can see the board isn't big enough. And then eventually you get back to another 180. So here's another 180. So the way that this pulse sequence and that this guy corresponds to here. So the way that this is notated in the interface is kind of confusing. So normally what we would have called the TR would be this. So that's what we would call really the TR. And so now the question is, what do we call the inversion time? Because, this would have been the inversion time here, like that. This is TI. That would be the time that you wait after the 180 until you do the RF pulse that's making your image. So this thing is kind of sort of the nominal inversion time. So sometimes that appears in the interface, but really what we want to know is like, what is the effective inversion time, which is what is the time until we get to the center of k-space? So this is, the TI effective. That would be the same as from the inversion pulse to the center of k-space here. This guy is TI effective. And the scanners differ on how they, let's put a boundary in between there. So here's because these times are not lined up. That's a little boundary. So here's the TI effective. It's the time when you get to the center of k-space. So the other thing is if you're on a Siemens scanner, they don't call this the TR. So let's put the TE in here. So there's the TE. So they don't. So the TR is going to be again something like 7 milliseconds, and the T is going to be like 3 milliseconds. But what Siemens calls the TR is this time. So this is TR Siemens. So it's not really the TR. The TR really is like, the time between these alpha pulses, but that's what they call the TR. And so what do they call what does Siemens call the real TR? They call it the echo spacing. So if you're on the scanner, the spacing between, so here's the RF pulse here. So here's the FID. Sorry. This guy is FID, which we're not recording. And here's the echo. So what Siemens calls the TR is so this is what they call, this is what is equivalent to the TR, because that time is the same as the time between the RF pulses. The same between the RF pulses is the same as the time between the echoes. This is what Siemens calls the TR, so they call it echo spacing. And that's equivalent to the TR. So it's a little It's a little confusing, unfortunately. But you can see how these things developed. They started off as the slow gradient echo is very straightforward. And then we do this sort of steady state where we do a bunch of ones where we can either spoil or not spoil. And then let's tack in an inversion pulse in this non-steady state thing. And then for the heck of it, let's patch up the magnetization in the phasing code directions, but not in the readout directions. And then let's rename everything differently from the other sequences. So, but why did we do this? Because the gray-white contrast is really good. And so this is basically a standard sequence that you use if you wanted to reconstruct the cortical surface using our cortical surface software. This is the sequence you would use. Okay, so any questions about MPRAGE? MPRAGE. So it's a sort of like a fast gradient echo, but we got some inversion, pulse. So this is, inversion recovery-like thing going on, and then, let's do some. So this is, grass-like, but not here. No fixer, not grass-like. So not grass-like here. Okay, so any questions about this sort of conceptual development of these sequences? So on Friday I'll talk about MP2 rage, because MPRAGE hasn't, there's a MP2 rage. We have that one on the scanner too. It's a useful one. Okay.